Hey there, I'm Zeina Kojok, and in this presentation, Jackie and I will be covering the graphic processing unit, the GPU, one of the most important components in a system on a chip besides the CPU. So let's start first with what is a GPU. GPU stands for Graphic Processing Unit and occasionally called Visual Processing Unit or VPU, and it is a dedicated processor efficient at manipulating or displaying computer graphics. A GPU is a specialized microprocessor that discharges and accelerates 3D or 2D graphics. It is used in embedded systems, mobile phones, personal computers, workstations, and game consoles.
But oftentimes people are more familiar with CPUs. So CPUs are actually made up of just a few cores. You can think of these cores as the power, the ability of a CPU to do certain calculations or computations. On the other hand, GPUs are made up of hundreds of cores, but what difference does it make? So, the thing with the CPU is that when it does a computation, it does so in a serial form. So it does one computation at a time. But with the GPU, it does it in parallel. So the importance of these two differences that with a GPU, you're able to do computations all at once and very intense computations at that. So oftentimes when you have app codes, a lot of it is going to be going to the CPU. But then every now and then you're going to have an application that's going to require quite a bit of compute intensive support that the CPU just can't do. So it's going to be offloaded to the GPU. So you can think of a GPU as that extra muscle or that extra brain power that the CPU just can't do on its own. CPU is optimized for minimum latency. So you want to be able to quickly switch between different operations. But the GPU is optimized for low throughput. So you want to be able to push as many operations through the device as possible. So just to give you an illustration here, in order to get the very low latency that you want to get on the CPU, there's a lot of infrastructures on the chip, like large caches to make sure that you have a massive amount of data readily available. There's a lot of control flow silicon to execute the stuff, and only a few parts that actually dedicated to compute. On the other hand, as you can see in the figure, on the GPU, the balance has shifted. We're saying we need hundreds of arithmetic and logic units, but the L2 cache can shrink because we are saying that it doesn't really matter how long it takes to get the data from the DRAM. That can take quite some time as long as you have sufficient work to hide that latency. So we need to make sure that we have a sufficient work to hide all the latencies that were introduced when fetching data from the global memory or when producing a complex operation. The idea here that there's no claim that one is better than the other. It's just we're covering different parts of the application with these different types of processors.
So, why use a GPU? In 3D graphics, everything is made up of triangles, lots and lots of small triangles that are built together to make complicated models. Now, as you know, a triangle has three vertices and it has a coordinate in the x and in the y and the z dimension. So one of the things that happen in 3D graphics is those vertices need to be processed, for example. They might need to be moved from one place to another place, that's called translation. Maybe it needs to be scaled to be bigger or smaller, and of course it can be rotated. Now, these three basic operations are called a transformation. It turns out in 3D graphics, the best way to express this XYZ coordinates is using a vector. If you want to perform a translation on a vector, you can multiply it by a special matrix, a special 4x4 matrix actually. Now, these matrices all have different properties. You can do scaling and transfer, translation, and rotation just using a particular predefined matrix. Therefore, a GPU is used for its power in vector operations, floating point operations, and matrix multiplication.
Now let's talk a bit about the GPU pipeline. The GPU receives geometry information from the CPU as an input and it provides a picture as an output. So let's see how that happens. We have different stages. The first stage is host interface, second, vertex processing, third, triangle setup, fourth, pixel processing, and the last one, memory interface. So let's discuss each stage alone. So let's start with the first stage, the host interface. What's the host interface? The host interface is the communication bridge between the CPU and the GPU. It receives commands from the CPU and also pulls geometry information from system memory. It outputs a stream of vertices in object space with all their associated information, texture coordinates, or per vertex color. As for the vertex processing stage receives vertices from the host interface in object space and outputs them in screen space. This may be a simple linear transformation or a complex operation involving morphing effects. But the main thing here is no new vertices are created in this stage and no vertices are discarded. Input-output has one-to-one mapping. The third stage is the triangle setup. In this stage, geometry information becomes raster information. This means screen space geometry is the input and pixels are the output. Prior to rasterization, triangles that are back-facing or are located outside the viewing are rejected. A pixel is generated if and only if its center is inside the triangle. Every pixel generated has its attributes computed to the perspective correct interpolation of the three vertices that make up the triangle. The fourth stage is the pixel processing. Now, each pixel provided by the triangle setup is fed into pixel processing as a set of attributes which are used to compute the final color for this pixel. The computations taking place here include texture mapping and math operations. As for the last stage is the memory interface. Pixel colors provided by the previous stage are written to the frame buffer. Used to be the biggest bottleneck before pixel processing took over. Before the final write occurs, some pixels are rejected by the Z buffer. On modern GPUs, Z is compressed to reduce frame buffer bandwidth, but not the size.
So now let's talk about shaders. Classic graphics cards are still relatively close to the graphics pipeline. With increasing demands on the GPU, restrictions were gradually removed out to create more flexibility. Modern graphics cards use a freely programmable shader control pipeline, which allows direct access to individual processing steps. To relieve the main processor, additional processing steps have been moved to the pipeline and the GPU. The most important shader units are pixel shaders, vertex shaders, and geometry shaders. The unified shader have been introduced to take full advantage of all units. This gives you a single large pool of shader units. As required, the pool is divided into different groups of shaders. A strict separation between the shader types is therefore no longer useful. It is also possible to use a so-called computer shader to perform any calculations of the display of a graphic on the GPU. The advantage is that they run very parallel, but there are limitations. These universal calculations are also called general-purpose computing on graphics processing units, or GPU for short. So now let's look where GPUs are used. But before that, there are two main providers of GPUs in industry, NVIDIA and AMD. Both providers manufacture GPUs that are optimized for certain use cases. So let's jump into that, because a big question is, why do we even need a GPU? In what industries and in what use cases? So the first thing we'll be talking about is VDI. VDI stands for Virtual Desktop Infrastructure. So GPUs are created to support high-intensive graphic applications. Think about it if you are a construction worker, right? And you're in the field and you need to access a very high graphic-intensive 3D CAD program. So rather than having the server right next to you or right in the field with you, you can have a server that's a country away in a cloud data center and be able to view that 3D graphic as if that server was right next to you. And that's going to be supported by the GPU because the GPU supports graphic intensive applications. Another example of this would be movie animation or rendering. So, in fact, GPUs actually first got their names mainly with the gaming industry. Oftentimes, they were referred to as gaming processing unit because of this ability to provide the end users with low latency graphics. But gaming is no longer the focus in industry anymore. It's a big piece of it, but now financial services, life sciences, and even healthcare are starting to get into it with artificial intelligence.
So artificial intelligence has two big pieces to it. There is machine learning and there is deep learning. So now there are also GPUs that are optimized and created specifically for those applications. There are some that are created for inferencing for machine learning purposes, and there are some that are created to help data scientists create and train neural networks. In other words, they're trying to create these algorithms that can think like a human brain. That's something that a CPU can simply do not do on its own, and it requires GPU capabilities. And then, lastly, let's talk about HPC. HPC is a buzzword that's been going around. It stands for high performance computing. While a GPU is not absolutely necessary for HPC, it's an important part of it. So, high performance computing is the company's ability to spread out their compute intensive workloads amongst multiple compute nodes, or in the case of cloud servers. Oftentimes, though, these applications are very compute intensive. It could include re-rendering, it could include artificial intelligence, and that's where a GPU comes in. You can add a GPU to these servers that are spread out amongst an HPC application and utilize those in that manner.
Now, there is one other thing we want to mention. That is, of course, there is a difference between 3D graphics on a desktop and 3D graphics on a mobile phone. Of course, if you've seen a 3D graphics card from Nvidia or from ATI, AMD, they are big. They've got big fans and big coolers on them. They need their own separate power supply sometimes. Now, of course, a mobile phone cannot do that. I mean, the Stratus cards themselves are bigger than most phones. So, of course, power efficiency is key when it comes to mobile GPUs. And that's why it's interesting that companies like Qualcomm and companies like ARM have actually seemed to be doing very well in the GPU market. But maybe NVIDIA isn't doing so well because it hasn't been able to translate its desktop GPU technology down to its mobile, whereas specifically designed mobile GPUs from, say, ARM are doing a much better job. Now, of course, the amazing thing is that we as consumers, we expect to see the greatest and best 3D graphics we can on a mobile phone because we're used to seeing things on a console or on a desktop, and the amazing thing is that GPU designs are managing to bring high levels of quality to a smartphone. Now, of course, you've always sensed to yourself when you're played a 3D game, the back of the phone does start to heat up a bit. And the reason for that is because of the parallel nature of the GPU and the CPU lit. If you're doing something, some of the cores might shut down. It might be only running at a few megahertz now, while there are power-saving things that go on inside the GPU at that time when you're actually rendering those 3D frames. It wants to get them out there as fast as it can. So all the shaders are working, all the stuff is going on so it can produce those graphic pinnacles. It's doing at 60 frames a second, which means every 60 milliseconds is processing a whole frame, including the word from the CPU and the GPU. And it's amazing that we can still actually get such great graphics from such a tiny piece of silicon and with such great battery life.